All right, good afternoon, everybody, and welcome to my presentation today on artificial neural networks. This is from Unit 1 of the unit on what is artificial intelligence. Let's get started. All right, so we're going to begin today with the basic question, what are neural networks? So neural networks are a subset of deep learning, what we looked at last time, and they're a computational model inspired by the biological structure of the human brain. We can see this within the aspects of the AI family tree that we've examined in previous lessons. So if artificial intelligence is the broad field of creating systems capable of performing tasks that typically require human intelligence, and machine learning is a subset of artificial intelligence that uses algorithms to parse data, learn from it, and make decisions without explicit programming. And deep learning, which we looked at last time, is a specialized subset of machine learning that utilizes the multi-layer neural network to solve complex problems. So the artificial neural network, or the ANN, the neural in the neural network comes from the biological neurons that are in the human brain. The neural network consists of these interconnected nodes or neurons that process information and learn patterns by adjusting internal parameters using math. So if we compare it with the biological, brain's neurons receive the chemical signals that reach a threshold and fire an electrical pulse to the next neuron in the human brain through the synapses within our brains. But the artificial model uses nodes that pass and receive signals, which are really just numerical inputs and outputs, and perform a calculation through math and pass the result on to the next layer of artificial neural network nodes or neurons. So let's do a reality check. While neural networks are inspired by the human brain, artificial neural networks are much simpler than that biological brain, and they rely on heavy mathematics rather than biological complexity to work. So, the artificial neural network is a computational AI deep learning model of interconnected layers of nodes, artificial neurons, that process data. The more layers in the network, the more powerful the model. So, from an initial input layer into the model, through a number of other layers to an output layer, that's the basic structure of the neural network. And we're going to examine this in a lot more depth. Those layers are based on a lot of mathematical theories like graph theory, and they use weighted connections, where weight is the strength of the connection between the nodes, very similar to the synapse connection between neurons in the human brain. And each layer performs a mathematical function and then passes the data or the number along to the next layer. The next layer then adjusts the weight to recognize intricate patterns, representations, and relationships in large hierarchical data. So, for example, this could be image recognition, or fraud detection, or natural language processing, or speech recognition. So, the neural network inspired by the biological brain uses mathematical theories like graph theory. All right, so now let's look at some of the ways in which the neural network actually works. So let's compare neural networks with graph theory. So graph theory is this branch of mathematics and computer science that studies graph objects. Graph objects we're familiar with as simple as the XY graphs. There are these structures that are used to model pairwise relationships. So despite the name, it isn't just about X and Y axis charts, but instead it's about a network of objects and how they are connected. But let's look at the components of a graph. So we have vertices or nodes. These represent the objects or the points. So this could be representative of things like people in a crowd, or cities on a map, or web pages on the internet, or in the case of neural networks, the individual neurons or processing units that hold that activation number. So the vertices or the nodes represent the objects or the points in the graph. The edges or the connections is the way or the path between the nodes, or an edge between vertices, right? They represent a relationship. Like, for example, in the analogy of cities on a map, they could represent roads that connect the cities. Or in the model of people in a crowd, the vertices, or pardon me, the edges or the connections could represent the friendships between those people, or hyperlinks between web pages. Or in the case of neural networks, we're talking about the way that the information flows from one neuron to the next, or from one node to the next. So we have two nodes with a connection, two vertex or vertices with an edge between them. This is all vocabulary that you can see in math, but you're going to see how that vocabulary relates to artificial intelligence. Now, within graphs, we have various types of graphs. So if we have two nodes with a connection, in this case, you see a connection between node A and node B, it could be what's called a directed graph. With a directed graph, now we're talking about information that moves or flows a specific direction. An undirected graph, which you see at the top of the screen there, is A and B are connected, but there's no direction to that connection. But in the graph below that, we see a connection that A flows its information to B, from A to B, but not B back to A. But then we see a connection between through B and C. And in this case, we can see information flows from B to C and also back from C to B. So information can flow one direction or both directions from one node to another across that edge connection. We can also have what's called a weighted graph. So with weighted graphs, the connection is assigned a weight or a value that represents the strength or the cost or the importance of that connection. So in one analogy, if we have our nodes representing cities and the edges representing the roads, then the number or the weight could represent the time it takes to travel down that road to reach one city from another, or maybe airline routes, or maybe the cost in terms of value. So that's a connection between nodes and determines the influence of one node has on the next. So we can have a basic graph, we can have a directed graph, we can have a weighted graph. In the artificial neural network, a high positive weight connection will excite or activate the next node or the next neuron in the neural network. A high negative weight would inhibit or deactivate the next node or the next neuron. So in other words, the number of that weighted value can have an effect on the node at the next layer. But we're going to see this when we get to a more detailed look at neural networks. All right, so let's just step back for a second. We've been throwing a lot of terms out here, but let's kind of get a summary here. With deep learning with a neural network, it's the process of finding the optimal weight value for the graph to solve a specific problem. But let's do some comparisons. In the human brain, we have neurons, biological neurons. In an artificial neural network, we have artificial neurons, which you could call nodes, or you could call perceptrons. In graph theory, they call them nodes. In the human brain, we have a synapse, which is a connection between neurons. In the neural network, we have a weighted connection, just like in graph theory, we have the edge, which connects the information through a flow. But in neural networks, we're weighting those connections. In the human brain, our synapses and neurons give slight electrical signals, whereas in the neural network, we're talking about numerical values to activate neurons, artificial neurons or perceptrons, and the human brain learns through synaptic plasticity, where the synapses between neurons become stronger or weaker over time. That's biological learning. Whereas in a neural network, learning takes place via updating of the weights. And as we'll see, that's a process we've already looked at called back propagation. So really within the realm of graph theory, what we're talking about is statistical values. We're talking about a branch of mathematics called statistics, which adjusts the values within the neural network. All right, that's a lot of terms. So let's now take machine learning and deep learning, and let's go even deeper into the internal components of the artificial neural network. All right, so let's start with the perceptron. That's within the realm of artificial neural networks, the name given to the artificial neuron. Now, we've used words like nodes and neurons, excuse me, but perceptron is the technical name for the artificial neuron or the node within an artificial neural network. It will calculate a weighted sum of all the inputs. So if that perceptron has a series of inputs, it will add them up, calculate them up, and then use three components to make a decision what output it's going to provide. Let's take a look at those decisions. So one, it's weights. The importance of each input has an influence on the perceptron. So if the weight of the input is 0, then it has very little effect on the perceptron. But if the weight is a positive number and it's summing all those inputs, that's going to have an effect. There's also something called a bias value in each perceptron. This is an extra value that's given to a perceptron that allows the model to shift the function up or down. Think of it as a way that you can influence the perceptron, or think of it as flexibility of that perceptron that can shift the result despite the input value. And then finally, we have what's called an activation function. So this is just a mathematical function or a mathematical gate that decides if we back up a step, those weights and biases, the number of inputs and their weight values, and the extra bias value, it'll determine if it's strong enough to be passed as an output to the next layer, whether that perceptron will activate or not. Now, there are various types of mathematical activation functions. They could include the ReLU function, which is if the input is positive, it passes it through, and if it's negative, it turns it into a 0. That's the ReLU function. There's also the sigmoid function. It squashes the value into a range between 0 and 1. So something like a decimal value, which is often used as a probability statistic, right? Like, is that a cat? 0.95 or 95% chance? Yes, it is. So that's the sigmoid function, which squishes a value into a range between 0 and 1. There's the tanh function. It's similar to the sigmoid function, but now it's squashing the output to a number between -1 and 1. So now it can go into the negative range. And that activation function introduces the concept of nonlinearity. So networks can learn complex patterns, with the basic formula being that you sum all the weights, all the inputs, and add the bias value, and then run it through that activation function. Okay, that's a lot of math. That's a lot of values. But these interconnected perceptrons, or these nodes, will eventually form an entire graph, or they'll form themselves into layers which create the neural network. So we're going to examine what are these layers and how do they lay themselves out. So the layers start with an input layer. So an input layer is a collection of perceptrons or nodes, okay? They will take an initial input into the model. So for example, this could be something like what you type in your prompt into ChatGPT. That's the input layer. Then the data is passed to a hidden layer, which is in the middle, where when it passes it, each node that it passes that data to will multiply all the inputs. So you can see in the graph here that that top green node or perceptron has 3 inputs from the 3 nodes of the input layer. It will sum all those inputs. It'll sum the weight of those inputs, add them all together. Then it will pass it through the activation function, which will include its bias. And it'll determine whether or not the output of that hidden layer node is going to be activated or not. So in this diagram, you can see only 2 of our hidden layer nodes will be activated. The other 2 will remain inactive. It will then pass that to another hidden layer, which will perform the same function. It will sum all the inputs and their weights, add in the bias, and then determine whether it will pass out through an activation function, whether or not each node in that hidden layer will activate or not. And in this case, only one of our nodes will be activated. And it will continue to go through more and more hidden layers. Weights are summed, they're scored again, the activation function is applied again, etc., 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 as it moves through each hidden layer of the neural network. So as the data is passed to each hidden layer in this process, it will continue to refine which node or which neuron is active. So it's like an incredibly complicated game of telephone, if you've ever played that game, where it's passing information to each layer, and it's refining it more and more and more, refining what we're getting to in our final answer. So these weights will act like dials that'll control the strength and the importance of each input signal, which in turn influences the nodes or the neuron's output signal. Those built-in biases are values that shift the decision threshold to determine that whether or not the inputs sum up or not, the bias can affect whether or not the nodes in the next layer activate, even with weaker input values. So the bias is yet another thing to factor in. The more hidden layers, the deeper the learning by the network. Finally, as it goes through hidden layer after hidden layer after hidden layer, the more hidden layers, the deeper the network. It'll eventually reach an output layer. The output layer is the final refinement of all those hidden layers, and that will produce the output or the model's prediction or classification. So in a simple example, if the input layer is the prompt you type into ChatGPT, the output layer is what ChatGPT shows you on the screen after you've typed your prompt by going through all those hidden layers. So the weights are summed, scored with bias, activation function applied, moves to the output, goes to the next layer, determines which nodes are activated by summing the weights, applying the bias, running through the activation function, passing to the next hidden layer, eventually reaching the output layer to give us the final output of what the AI model is trying to do. So neural networks are designed in this way, and they're going to be learning using the training data that we examined in our previous presentations. So this could be labeled or supervised data. This could be unsupervised or unlabeled data, and it can even be semi-supervised data. And it's going to move that training data through the layers. When we get to the output layer, if the model's not giving us exactly what we want, then error calculations are made to calculate the discrepancy between the network's predicted output and the actual correct or expected output. So obviously labeled data and semi-supervised data allow us to see and make those error calculations. This, along with weight and bias adjustment, will retrain the data in the neural network to account for those errors and discrepancies. And let's recall that this process of retraining or going backwards through the neural network is called backpropagation. So let's use the archery analogy that we used before to try and reinforce a lot of these concepts. All right, so in backpropagation, there's what's first called the forward pass. So let's use our archery analysis, okay, and the analogy of using archery. So the archer will stand up, take his bow, take his arrow, look at the target, pull back the string of the bow with the arrow loaded in, and shoot the arrow. And let's say it lands at the target 10 inches away from the bullseye. So it's not a perfect shot. The archer's input was taking the arrow, preparing, shooting, and the output is where the arrow actually lands. So that's our first attempt at shooting the arrow to the bullseye. It's our forward pass. So now we take the arrow and calculate how far away from the bullseye it landed. So we notice there's a 10-inch gap. This is our error. This is our loss function. We calculate and measure the distance we were off from our target. That loss function will quantify, put a value to how wrong we actually were, or in this case, how far off the archer was. Now, the feedback process, the backpropagation, is we're going to go backwards through our process to make subtle adjustments to, in this case, body mechanics. So maybe we released the arrow too early, and that's why it went a little left and it was 10 inches away. So we noticed that it was 10 inches away, we calculated that loss, and we're realizing that we released the arrow a little too early. Why did we release it too early? Well, maybe our back elbow was raised up too high. And because it was raised too high, we released early. So that's one of our hidden layers. Yes, we've realized that we released too early, but hidden within that was the fact that our elbow was too high. And maybe our elbow was too high because our stance was too wide. Our feet were too far apart, which caused our elbow to be too high. So these would be the hidden parts of the process that we're going to make subtle adjustments to. Maybe we're going to bring our feet closer together, which will result in our elbow dropping down slightly, which will result in us releasing the arrow a little bit later, which will result in us not being 10 inches away from the bullseye, but maybe being 9 inches away from the bullseye. And then we'll go through the back propagation process again to make even more subtle adjustments to see if our error loss function calculation is getting closer and closer to the bullseye. So it's an adjustment. Adjust the stance, adjust the elbow, adjust the release by a tiny fraction through back propagation to try and get a little closer to our goal. So the artificial neural networks, which are a subset of deep learning, which is itself a subset of machine learning, which is itself a subset of artificial intelligence, are inspired by the human biological brain and consist of artificial neurons called nodes or perceptrons. Those perceptrons contain a weight, they contain a bias, they contain an activation function. They're connected to other perceptrons. So perceptrons form a layer. This is based on graph theory and statistics. Each layer forms the neural network. The layers of that artificial neural network will include an input layer, many hidden layers. The more hidden, the deeper the learning, hence the term deep learning. And finally, an output layer. From our standpoint as artificial intelligence users, we use something like a prompt in something like Gemini or Claude or ChatGPT. We provide the prompt input, which is the input layer. It provides all the middle hidden layers. It provides the perceptrons arranged in layers. It provides the weighting and the biases and the activation functions. We don't need to worry about all that. Eventually reaching an output layer, which is what we see as the result of our prompt input. It uses back propagation to learn through training data to get better and better at getting closer to our goal, like our archer was getting closer to the bullseye. So that back propagation flows the information in the opposite direction of the calculated output. It calculates error by comparing the prediction to the correct labeled answer. It assigns essentially blame. The back propagation uses calculus, specifically within calculus, the chain rule, to calculate gradient descent, how much each specific weight and bias contributed to the error. And it will update by going backward from the output layer backwards to the input layer, making subtle adjustments to each weight and each bias in the direction that will reduce the error. Thank you, everybody. I know that was a lot of math and a lot of information about the inner workings of the artificial neural network, but I hope you learned a lot, and we'll see you next time.